Hello everyone, this is Vahe. We will go back to Matlab again. So we'll do some Matlab work and we will use Matlab to work on some particular elements of Matlab which we haven't used. One of them is called functions. In other words, how to write your own function. You know that there are built-in functions like sine, cosine, etc. But how to write your own function. So we'll experiment with a little bit of that in this experiment. And we also want to know a little bit about scripts. So MATLAB scripts are just nothing more than, a series of commands that you want to type in one sitting or once going through together instead of one at a time. So if you want to if you're typing in the same 10 commands over and over again, how do you automate that? So that's what a script is. It's a series of commands written back to back. And you can do some nice things with that, and it makes your program reusable later on. Now, we're going to use some of the material that we learned as well, so items like voltage division, current division, and instead of just working with real numbers, we'll also work with complex numbers because we've had enough practice with complex numbers as well. So we'll try to explore all that. Before doing that, let's get to the MATLAB input, and let's look at some things that you may or may not be aware of. So here's the MATLAB input, and typically, when you come in, this is what you're seeing. Pay particular attention, close attention to this directory up here. That's called a working directory. So anytime you put a file in that directory, MATLAB will recognize it. So MATLAB has that directory under its search path. So scripts and functions that I just talked about are most efficiently located under that directory, and it makes it much easier to run if the files that you generate, custom generated files, are put into that directory. You can always change the directory as well. For example, you can easily change this directory to be your desktop EC115 directory, and you may put your files in that directory. Okay, so first of all, let's look at a couple of functions that are particular to MATLAB. So in particular, we know we can write real numbers. That's not a big deal. But as you know, in MATLAB, we can write either I or J, and MATLAB recognizes that as a complex function. Like, for example, we say z equals 3 plus j times 4, right? We know it's a complex number. And once we enter it, you'll see that MATLAB recognizes it. The only thing you'll see is that MATLAB will reply with I, because MATLAB recognizes I and J, but it will always reply with I. So just note that. Also, it writes the I after the number instead of before the number like we do for our notation. Okay, so once you have a complex number like this, 3 plus J4, where is that? Well, it's in the first quadrant, right? 3 is the real part, 4 is the imaginary part, right? Anything that multiplies the I or the J, it's the imaginary part. The real part is the real part, obviously. And now, if you want to generate the magnitude, if you want to calculate the magnitude of this complex number, you can simply use ABS. That means absolute value. So it generates the absolute value of this Z, okay? And you'll get 5, because it's 3 squared plus 4 squared square root, right? So that's where that's coming from. On top of that, we can look at the phase or the angle, right? Angle of this complex number. So we can say angle of Z, okay? And you'll get 0.9273. Notice that this angle is in radians. So if you want to have the angle in degrees instead, there are a couple of options, okay? You can take the angle, okay, and then you can multiply it by 180 and divide it by pi, right? So we're basically multiplying by 1, right? Because 180 over pi is 180 degrees over pi radians is really 1. So this gets rid of the radians. So this will give you 53.13 degrees. That's one way to do it. Another way to do it is use the function called rad to degree. So radian to degrees and if you put an angle of the z, right, you'll get back also the same thing. So the second thing that I typed in, rad to degrees, this is a built-in Matlab function. So you can say rad to degrees and in parentheses put something that's in radians and it'll give you the. So either one of these is fine, but just realize that when you say angle z, you're going to get the angle in radians. Okay, so that's one thing you should know. The other thing you should know is that Matlab accepts both rectangular inputs as well as polar inputs. I mean, just to go back and make you kind of aware of this, I have a reference sheet for you that I'm gonna also locate. So when we have z equals a plus jb, that's rectangular form, and we can convert it to polar form, right? And the polar form is represented by an amplitude and an angle, right? So the a and the theta represent the amplitude and the angle, and we can represent that two ways. You can write a e to the j theta or a at the angle theta. These are equivalent notation, right? So when you say a e to the j theta, I mean, by using Euler's identity, we know that e to the j theta is cosine theta plus j sine theta. So we can rewrite it this way. And so a cosine theta is the real part, and then a sine theta, the thing that multiplies j, is the imaginary part. So you should know all this, but what I want to point out is that we can also enter the complex numbers with the exponential or polar notation. So let me show you this in Matlab, okay? So in Matlab, if you want to put on complex number, let's say the complex number has a magnitude 2 and an angle of, let's say, 60 degrees, okay? So let's say amplitude of, you can pick anything you like. Let's say amplitude is 5. Okay, let me just pick something else. So 5 e, so this is exponential. This means e to the some angle, j times the angle. Now, angle you got to put in radians. So we're talking about 60 degrees. That's pi over 3. So this complex number that I just written down has an amplitude or magnitude 5 and an angle of 60 degrees. And when you press enter, you'll get the rectangular version of that. But basically, those are equivalent. On my reference sheet, I have also given you information regarding that. So here's some angles, typical angles in radians and degrees, their cosines and sines. Here's the Euler formula again for e to the j theta, e to the minus j theta. Also some quantities here for j squared, some simplifications. So pretty much everything is here as a reference for you, but just remember that the rectangular and the polar forms represent the same complex number in the real imaginary plane. So that's one thing to know. And you should be able to go back and forth between them pretty easily. And what I'm just showing you here are the built-in functions that you can easily do that with. Okay. So I hope that's clear. And we can verify a lot of these things. For example, where does this 2.5 come from? Well, that comes from 5 times cosine of pi over 3, and 4.33 is 5 times the sine of pi over 3, right? So you can say the real part is 5 times cosine of pi over 3, right? That's your 2.5, and 5 times the sine of pi over 3. Okay, that's your 4.3301. So you can see how that's done. Now there's another function that you may or may not be aware of. Again, when you say sine of something or cosine of something, that's something you're taking the sine or cosine of. That's really in radians. So as I illustrated, you can say cos pi over 3, right, is a half. So you're getting a half there. Cosine of 60 is a half. And by the way, obviously, you can go back here and check that. Cosine of pi over 3, 60 is a half right there. Okay, so you can check that. Those are the things that table is something you probably should know because it's very, very common to know those angles, very easy angles. Anyway, another way you could do this, get the cosine of 60 degrees, is to use the modified version of the cos function. So if you say cos d, okay, cos d, then you can put the actual degrees in the parentheses. So you can say cos d 60. Okay, that's okay. That should give you the same result, a half. Okay, so you can use cos or cos d. When you say cos, it expects radians. When you say cos d, you can put actually degrees in there. So similar things are true for sine, right? You can say sine d, for example, sine d 60. Okay, sine of 60 is root 3 over 2, right? That's 0.866. That's about root 3 over 2, right? We can just check. Square root of 3 over 2, right? Makes sense. So some things like this you should really know. And I mean, all I'm really doing is I'm using Matlab as a very, very fancy calculator. You should be able to calculate these on your calculator, obviously. But I'm showing these functions because these are what you can use when you are using Matlab as a programming language, so to speak, and when you're writing a script, for example. Okay, fine and dandy. So I think you already know how to deal with the complex numbers now, get the magnitude, get the angle, so on and so forth. All right, so let me now talk about something a little different, namely how to use Matlab to write a new function, or a custom function, okay? And for this, I'm going to show you an example that I'm actually going to be sending to you, so there's no really need to write this. But there's so few lines that I don't think you would have much problem writing it either. But let me just show it to you. Like, first of all, I'm going to send you a couple of files. Send you meaning that they're going to be posted on Blackboard. You'll just download them and, for example, put them in your EC115 directory. There's 2 files, okay? So let me actually do that, okay? So let's say you put those 2 files in your EC115 directory on your desktop, okay? So let me navigate there. So let me go here. It says browse for folder, okay? So I'm going to change my working directory where the Matlab will search for functions, okay? And then I'm going to go to my desktop, okay? And I have EC115 there. I'm going to select that as my folder. When I do that, I'm going to have these 2 files. So what I'm going to actually do with is I'm going to deal with the first file first, okay? It's called part2.m. So I'm going to just double click this. And when you double click it, okay, this editor comes up. So Matlab has its own editor. And the nice thing about this is that it tells you when things are right or wrong, when you're using the right syntax. It has what's called syntax highlighting. So if there's a keyword, it puts them in blue. It puts the comment, for example, anything after the percentage symbol, it puts it in green, which means the comment is not read in. So very much like a programming language. Okay, so what does this function do? Okay, so what I have done here is I have defined a function called part2. As you notice, the name of the file is part2, as well as the name of the function, which appears right here. So that's part2 is the name of the function. And the function is defined by this function and end statements. Between this is where the function is defined. So the way this goes is the function of part2 takes in 2 inputs. Okay, the thing in the parentheses are the inputs that are going to go into this function. Okay, and I'll illustrate to you how you actually use it. But the part2 has 2 inputs and it has 1 output. The output is on the left side, okay, just like an equation, and it's being shown in this square bracket. So the output is called REQ, and the inputs are R1 and R2. Now, how do we get REQ from R1 and R2? Well, this particular function, what it does is, if you give it R1 and R2, it computes the parallel combination. So how do you get the parallel combination? Well, you do 1 over R1 plus 1 over R2, and you take the inverse of that, right? And that's exactly what's going on in this equation. Very, very simple, right? But that's all that's going on here, all right? Now, once you define this, okay, once you define it this way and you save it, which I've already done, and you see it in this left side directory, then you can use this file, you can use this function, you can use this function as if it was a built-in MATLAB function, okay? As if it was a built-in MATLAB function. So I hope you see what's happening, right? There's 2 inputs, there's a single output. That's a function that defines the output as a function of the input, right? So now I have this thing called part2. So here's how it works. Let me get rid of this so you can actually see what's going on down here. So I'm in the MATLAB window now, and with this directory highlighted, with this directory being the working directory, anything in there is now visible. So let me just clear the screen so you can see it easier. So now I can use this function called par2, and the way I can use it is I can use it like this. I can say par2, and then I can give it a pair of resistors. Let's say I use, and in fact the help tells me exactly what I need to do. I need two inputs. So let's say I put in, I know, 3, 6. That does 3 parallel 6 for me. Okay, and I know what 3 parallel 6 is. I happen to know for 2 parallel resistors, it's the R1, R2 divided by R1 plus R2, right? That's going to be 18/9 or 2 ohms. There it is. Okay. I can try different things. I can say, okay, let me put in, I don't know, 12, 24. Who knows what that is, right? Apparently it's 8. Okay. Anyway, you can try this and see if it's working, right? But this is the starting point. Remember, the function that actually allowing us to do this is this, right? So this is not a built-in Matlab function. We just made it ourselves, and now you can imagine how you can make your own function for other things. Let's say we had 3 resistors in parallel. How would you do that, right? I'm sure you can imagine how you could do that. Maybe you would have 3 inputs, rename the file as part3, for example. Have 3 inputs, call it R equivalent, whatever. You can see how you may modify it. In fact, we're going to ask you to do that. Okay. Now, there's a couple things. Okay. So first of all, even though I actually did this for just R1 and R2, this also works for impedances, Z1 and Z2. And if you notice this comment, I tell you exactly what's going on. In other words, let's say I had an impedance of J2, okay, from an inductor, and let's say 4 ohms, right? I could take the parallel combination of that, right? Let's say I had J5 and minus J3, right? I could do the parallel combination of that. Let's say I had 2 plus J2 in parallel with 2 minus J3. I could take the parallel combination of that, right? Because the parallel operation is still the same. It's product over the sum, and this function will happily do that with no problem. So for example, let's say we said par2, right? Parallel of 2 elements. One element is 3 plus j times 5, right? And the other element is, let's say, 4 minus j times, who knows, 2 or something. I'm just randomly picking something here. Press enter, that's the parallel combination. Okay? Very easy to do. Okay? So you can experiment with this and see what happens, okay? And it will work. It'll work each and every time. So that little function that we wrote is actually quite powerful, and it saves you a lot of time, because if you try to do this by hand, you'll see how long it takes. Does that make sense to everybody? Think about that. And think about how you can modify this for, in other words, how you can modify this for 3 elements, or 4 elements, or 5 elements, right? It's pretty easy. It's actually pretty easy, okay? Now, there's another thing about functions. Once you define a function like part2, okay, then it's available not only through this interface that I'm seeing, but I can also put it inside the program, inside another script, inside another function. So a function can refer to another function. Just to show you, let's say I wanted to take the parallel combination of 3 resistors. Okay, 3 resistors. So let's say I had a 3 ohm, 6 ohm, and a 2 ohm. 3 ohm, 6 ohm, and a 2 ohm. Now, I can just do what I did before, right? I can do this, right? 3 parallel with 6 is 2, and 2 parallel 2 is 1, right? So if I do 2, 3, and 6 in parallel, I'm going to get 1. Check it out, right? That's true. But I don't have a par 3, right? I don't have a par 3. I don't have a parallel 3. So how do I do that? Well, I can go back and do what I asked you to do, which we're going to ask you to do a new function for par 3. Or you can use par 2 twice. Let me show that to you. Okay, so you can do something like parallel combination of 2 resistors. One of the resistors is just 2, and the other resistor is parallel resistor of 3 and 6. Does that make sense? Right? So if you look at this inside here, the second value, the second input, is itself another 2 input calculation. So part 2, 3, 6 gives us 2, and then part 2, 2 comma 2 will give us 1, right? So there you go, right? So you can nest the functions as well. Again, very simple things, but if you use them the right way, this will allow you to solve quite a number of complex problems. So I'm trying to show you very, very simple things, and it looks simple, but it's up to you as to how you may want to use them in the course, in the future, etc. So I'm trying to give you a lot more than just the simple things and just opening up the ideas. So I hope that makes sense for now. And I think with this you should be able to write a function and use functions if they are asked on the experimental procedure for experiment number 7. Okay, now scripts. Let's get to scripts. What are scripts all about? Well, again, as I said, scripts or Matlab scripts are just a collection of functions or collection of commands written back to back to back, all collected together, that are saved in a single file that we can run at once. Okay, and I'm going to illustrate that with one that I've written here. It's called voltage division. But before going into that, I want to show you something. Right? For example, there's some things that allow us to, for example, ask the user for input. So let's say you're running a script, running a little program. We can ask the user to input some information. Like, for example, let's say we're going to do voltage division. And in fact, that file I'm going to show you next is voltage division. Let's say we want to ask the user for the voltage source value Vs and then the two resistor values R1 and R2, right? So let's say, for example, we're going to ask the users to enter the Vs value. We may do something like this. We may say that Vs is input by using the command, believe it or not, input, that we ask the user, and inside the simple parentheses or single quotes, we say, for example, enter voltage Vs, and maybe we'll leave a little colon here. We'll leave a little space. You'll see while we need that space, close the single quote, close the parentheses, and if we press enter, it says enter voltage Vs, right? Now, if I hadn't left that space after the colon, that prompt would have been right next to it. It's too close, right? But anyway, if I put in some number, let's say like 12, press enter, now Vs is set to 12. In fact, if you look at the upper workspace here, it says Vs is 12. So now I've entered Vs equals 12, basically, right? But I got it not because it was a constant, but I actually queried the user. I asked the user, and the user enters it in, right? Imagine doing the same thing for R1 and R2. Now, so that's a way you can ask the user for inputs, and then we can calculate for different situations. Now, the other thing we can do is that after we calculated things, for example, by using voltage division, etc., we can actually provide that information, provide the calculated information to the user with a text, okay, with a text information. Let me give you an example of what I mean. Let's say we calculated V1, right? Let's say we said V1 was equal to, who knows, maybe it was like 3 divided by 4 plus 3 times Vs, right? Some kind of voltage division expression like this. You press enter, and that's the value for V1. But let's say we just don't want to report the output like that, but we want to say something like, the voltage across R1 is V1, or the voltage V1 is equal to numerical value of V1 volts. How we do that? We would do something like this. We would first form the text of what we want to say like this, okay? So we say Vs text, and then we basically concatenate, put together all kinds of string information. So let me show you. So we'll say, for example, Vs text, okay, we'll say, let's say the voltage across R1 is V1 equals, and we'll leave a little space and you'll see why, okay? And then we'll say plus, and then the actual value of V1 is just V1, okay? The thing inside the double quotes is a text. You can make that anything you like, okay? And then we'll say volts here. Sorry, volts. Okay, so this is the text. Okay, how the user, well, what the user will say. It'll say the voltage across R1 is V1 equals 2, and there'll be some numerical value represented by this over here. In this case, it's going to be 5.1 volts, right? So if you press enter, you'll see that this is what the user will be presented with. Okay, it'll say the voltage across R1 is V1. So in other words, we can use these kinds of information to input information from get input from the user, do our calculations, and then present something to the user. So these are what are kind of what we find in scripts. Okay, this kind of information. So it's a calculation that's done over and over and over again. And so what we do is we just kind of put it together and make it look pretty. Okay, and then we even add some comments in there to remind us what all the calculations are. It's nice, and it stands by itself, and if you go back to it, you'll be able to read it and modify it. Okay, so let's take a look at this called volt_div.m, voltage division. So if you click on that, you get this what we call a script. Anything after the percent, anything to the right of the percent is a comment. It is not read in, it is not computed. Okay, so those you see in green, anything in green, okay, anything that you see in green is a comment. So this basically, what it does is it displays voltage division. Okay, just when you run this script, it'll say voltage division. It'll ask you for Vs. Okay, it'll ask you for R1, it'll ask you for R2, and it'll just calculate the two voltage division expressions, V1 and V2. Okay, and then it'll provide these text files exactly as I showed you. Okay, with little modification here and there, a little space maybe. Difference is maybe a little space in front of the V, but other than that, it's identical to what I showed you. And then it'll just display the results, right? So if I had gone down here, if I had said DISP and then say VS text, it'll just display that text exactly, not removing the quotes basically. Okay, so that's all this thing does. It asks the user for VS R1, R2, computes the voltages, okay, sets up the strings to be displayed, and it displays the strings as results. That's it. All right, so let's see what happens when we run this. Okay, now how do you run this? The way you run it is, assuming this file name volt_div appears in the directory, your current folder, okay, you just type its name. You just type its name. You just say, and let me get rid of this for now because you know what it does basically. You know what volt_div does. So let me clear. Okay, so if you type in volt_div or whatever you call the program and run it, it'll say voltage division, enter VS. I just put in a value, let's say 10, right? 10 volts. R1, okay, 2 ohms. R2, 7 ohms. And those are the V1 and V2 values. Very, very simple, right? I mean, you know what's at the guts of the program, but if you use these kind of processing power, the string processing power, you can really save yourself a lot of time with certain kind of problems, okay? Because unlike the Matlab command window, which we're in right now, which we'd write command one after the other, after the other, after the other, right? That's not really the way to do it. In fact, in experiment number 2, you saw those programs that we ran. Okay, those were all scripts as well, right? Those were scripts. Okay, those were scripts. But now we'll ask you to write your own. Okay, and we're gonna ask you to write your own scripts on things that you know. For example, current division, voltage division, equivalent resistances, etc., etc. Okay, now here's something else. Just like what I showed you with the parallel combination function, which was originally written, right? Let's take a look at how it looked like. This was originally written for R1 and R2, but it works for Z1 and Z2 as well, provided you put in complex numbers. Same goes with this voltage division. It works for VS R1, R2, but it also works if you have phasor VS, right? And R1, R2, or Z1, Z2 for that matter, right? They can be complex. So these things work just fine with complex numbers, right? Let's just work it through. Let's run voltage division again. Okay, voltage division. Enter Vs. Okay, I'll put in, let's say, 10 at the angle 50, right? Or 10 at the angle 60, or 10 at the angle 70, whatever it is, right? The only thing is I have to write it in radians. So let's say 10 at the angle 60, okay? So that I can write by 10 times exp j, right? J times the angle. 60 degrees is pi over 3. Okay, so that's my 10 at the angle 60 input. R1, instead of R1, I can put an X1. For example, that could have been J times 10, right? R2, that could have been maybe 30 ohms, 40 ohms, or minus J something. It could be anything. Could be anything. Press enter, and there you go. Voltage across R1, voltage across R2. Those are the complex valued functions, right? So if I go to V1, for example, that's your V1. Let me just show it to you again. Here's V1, right? That's your V1. Well, what's the magnitude of V1? ABS V1. That's the magnitude. What's the angle of V1? You say angle of V1. Now the thing is, that's in radians, right? So maybe I want that in degrees. Two ways of doing it. You multiply by 180 over pi, or you can use the rad to degree function. Let's just use the rad to degree function. So here's rad to degree. And it's 135.963. Or obviously, you could have done this. We can check. If you multiply the angle by 180 over pi, you should get the same thing. And you do. Okay. So I hope all this information is useful to you. Again, I'm going to send you these two files, part 2 and volt div. Okay, part 2 and volt div. You can take those files from the Blackboard site and simply put them in your EC115 directory, and make sure you change your working directory to your desktop EC115 directory, as I have done. They'll appear here and you'll be in business. Okay, very easy. So that's one thing that you'll have are these two files. Okay, the other thing you'll have is that I'll give you this document, which is like a summary. There's nothing really completely new here. You're gonna know everything in here, or you should know everything in here. It's just a reference, okay, for you to have when you're doing calculations. It might help you in other things too. Okay, so I'll send you this. And in addition to this, I will send you obviously the experiment, the procedure. That will also be there. But for now, if you watch this, I think it'll be quite helpful. If you watch this video and maybe go over it again, I think you should be pretty much ready, because this is just building on your knowledge of Matlab and the complex analysis and the phasor analysis that we've been doing with circuits. So I hope it puts it all together, and it also shows you how you can use Matlab in different ways, using complex numbers, using functions, and using these scripts. So I thank you for your attention, and I hope you have a wonderful week. Hope everything is going well. Bye-bye.